Okay, optimizing cost. A cylindrical chemical storage tank with a capacity of 1,000 meters cubed is going to be constructed in a warehouse that is 12 meters by 15 meters with a height of 11 meters. The specifications call for the base to be made of sheet steel that costs $100 per meter squared. The top to be made out of sheet steel that costs $50 per meter squared. Oh, cheaper stuff on top. And the wall to be made of a sheet steel that costs $80 per meter squared. First, determine whether it's possible for a tank of this capacity to fit into the warehouse. So we're going to have to figure out what our restrictions on the radius of this. We said it was a cylindrical chemical storage in a warehouse. So let's get a visual for what they're talking about. Let's see if I got a rectangle. Perfect. So let's say we have our rectangle here. That's not what I wanted. Move it there. Delete this. So they have some type of storage unit, which we're going to fit a cylinder into. They said that this thing was 12 by 15 with 11 meters in height. Okay, so definitely not to scale. I apologize. But that's the idea. Okay, 12, 15 with a height of 11. Yes, okay, so they were very specific in the height. We need to fit a cylindrical storage tank inside. Oops, wrong one. Let's do the oval. So we have to get a storage tank in there. Let's just fix that. That looks something like this. And let's move this over so it fits. There we go. Okay. Now, we're going to have to put some restrictions on our tank. First of all, what is the height of our tank at max going to be? Okay. So we have 11 meters at max. Now, because this isn't a square here, we have a restriction on the radius. What is the largest the radius is going to be able to be in this question? And how do we get 6?
Because you take the 12, because since the circle's radius
Right.
is constant.
So the diameter of this circle at max can be 12 meters, right? That way it fits across here. It'll have room to go back and forth there, but it won't be able to get any wider without hitting the walls, which means our radius is half of that. So our radius is 6 meters in length. So we can definitely make something of this size. We can fit it into here, okay? Now, this question is broken into a question with prices based on surface area. So let's get into surface area of this cylinder, okay? So the surface area of a cylinder is the area of a face, so that's our pi r squared. Because there's 2 faces, it's multiplied by 2, plus the area of the rectangle that's wrapped around. Now the length of that rectangle is the circumference of the circle. So that's 2 pi r times the height, which would be the width. So this is your formula for surface area of a cylinder. If you have trouble, I can explain it again a little after. Okay? We know that in this case, our radius is going to be a max of 6, and our height is going to be a max of 11 in this question. So what we want to do is we do want to get a cost function also. Okay. Our costs are very important. The specifications call for the base to be out of 100 meters, $100 per meter, $50 per meter, and $80 per meter. So we have the base being $100 per meter squared, the top being $50 per meter squared, and the body being $80 per meter, squared. This is going to change things. Though we can definitely fit this in here, this might not be the exact shape we want to make depending on what the costs are going to be for us. So we're actually going to split this into 3 things because the cost for the bottom and the top are very different. So we're going to split these numbers and put in our prices. Okay? I think they wanted a cylinder. They said in the question they wanted to be a cylinder. So what that means is this now becomes one of the costs So our cost times our area. Since this is the area of one of the faces, pi r squared, multiplied by the cost being 100. I'll put these in colors for us, okay? So our cost is $100 for the one on the bottom, pi r squared. So that's taking care of the bottom face. The top face was, we'll do in blue, $50 per meter squared. So that's $50 times pi r squared, okay? And finally, the body of this was $80 times the area, which is 2 pi r h. Okay? So what we're going to do here is now we're going to simplify what we have. We have these two can be added together to be 150 pi r squared. And this here becomes plus 160 pi r by h. Okay? So now this is our new formula we're going to be working with. And we're not going to be plugging in our value yet. We have a max restriction on our radius of 6. And what's the smallest the radius can be? 0, right? We're also going to see if there's any critical values between those. So we're going to derive this in terms of our r, which means we're going to have to get a value for h to plug in.
Sir,
Mm-hmm.
that should be C now, right? Since you changed it.
Yes, you're right. This is no longer surface area. This is now our cost function since we plugged into our cost involved. Okay? So what we did leave out is they told us that the volume, and the volume of a cylinder is our pi r squared times h. Is that right? Area of the face is pi r squared times h. Yeah. So this is our area, or sorry, our volume formula. They also said the volume would have 1,000 meters cubed. In other words, we can replace V with 1,000, which is equal to pi r squared times h. And because we're trying to replace h in this question, we're going to isolate this for h. So h is equal to 1,000 divided by pi r squared. So we now have a value for h, which you can plug into our cost function. Okay? So now our cost function will be solely in terms of r. So what I'm going to write this as is c, the cost, in terms of r, the radius of this, is going to be 150 pi r squared plus 160 pi r times 1,000 over pi r squared, which we can simplify this a little. This still stays as 150 pi r squared. This 1,000, well, that makes it a very large number. 1,600, 3 more zeros is, oops, no, 1, 2, 3. We don't need that. 160,000. And here both of our pi's will cancel out, and our r on top will cancel out to only have a r on the bottom. So it's 160,000 over the value of r. This is our new cost function solely in reference to the radius of this cylinder. Now that we've done that, we know our critical values are between 0 and 6. Okay? So because of that, we need to find to see if there's any other critical values involved. So we're going to derive this function, the cost function in terms of r. When we derive this, this will become 300 pi r. And this will become negative 160,000 over r squared. Okay? So this is a derivative of our function now. So when we do this, we're going to go about trying to solve this function. So we know that whatever our cost is, if it was a constant term, we set it equal to 0 here to find out what r would be when the radius has a critical value. So we have 300 pi r minus 160,000 over r squared. We bring over our negative 300. Pi r is equal to negative 160,000 over r squared. I can bring over r squared, which would give me negative 300 pi times r cubed. It's equal to negative 1,600. Okay. Which would then give me r cubed is equal to positive, we'll get rid of 2 of those zeros, 1,600 over 3 pi, and I bring the pi over. So we have 1,000 over 3 pi, And we have to find the cube root of this value to find our radius. So our radius in this function, anybody have a calculator there? Let's know, maybe so. Okay, I'll try it on mine here. 1600 divided by, oh, I wrote that wrong. Oh, that's easier. By 3 pi. Is that right? That's I don't think that calculator worked out. The calculator I have on here isn't the nicest. Let's just do. What did you get for a job? 5.5? Approximately 5.5? Okay, great, thank you. Sorry about that long wait. So, our radius is 5.5, which does fall between 0 and 6. Okay. And so what we're going to do in this question is we're going to test all three. But are we? A radius of 0. Is that helpful to us at all? No, definitely not a possibility. Is 6 a possibility for radius? Yeah, 6 is. We could just make it to its maximum width, right? So we're going to only test 2 of them. We don't have to test the value of 0 because we wouldn't have a cylinder at that point. So we go to our cost function. Our cost function is the important part here. This function here. The simplified version when we had h involved. Okay? I'm going to copy it. I'm going to paste it at the bottom, and we're going to plug our values in. Okay. So our values, we're going to test at 5.5 and 6. So our cost, when the radius is 5.5, would give us 150 pi times 5.5 squared plus 160,000 over 5.5. So that will give us one cost. And our second cost is at the value of 6. 150 pi times 6 squared plus 160,000 over 6. Hopefully you guys can help me out. My calculator is not a 2-line calculator on the computer. Should really invest in one. 36 times pi times 150 plus bracket. Is that right? $43,631? $631. Did anyone get the first one? 17,100. Oh wow, that's a huge difference in price. Yeah, from 0.5 of a radius because of our material having such different costs. 42? Or 44? Oh, 43,344. I feel like that might be a little closer because somebody double check it for me. This seems like that's a huge difference. I think this might be it. That is? Okay, that makes a little more sense. So it's $300 cheaper, not $30,000 cheaper, to have a radius of 0.5 less in terms of our cost, okay? That's because of our top and bottom and our sides of our object having all three different costs.